We left off at this, applications of probability. So let's go to the applications. Basically, simple verbally described problems. We want to see how to handle that. Example 7 says, card, let me clear the board first. From a deck of cards, card is randomly drawn. E is the card is a spade, and F is card is queen. And first question is, are they mutually exclusive? Explain your conclusion. Okay, so they're not mutually exclusive because remember, to be mutually exclusive, the intersection should be empty. There should be nothing common so that both events should not happen at the same time. But these two events can happen at the same time. There is something common, and that is Queen of Spade. Queen of Spade is there in both E and F. So therefore, it's not mutually exclusive. Part B is find the probability for the event card is spade or queen. So that's the union. So that's probability of E union F is what we need to find. So we don't need to write down the individual events, but we need the count of the event, E union F, and divide it by count of sample space. The count of the event is event E has spade, all the spades. So that'll be 13. There are 13 spades. So there are 13 cards in E. F has queen, so that's 4. 4 queens. There are, from each kind, there is one queen from each kind. So 4 queens are there. One of those queens is already in E, which is the queen of spade. So therefore, there are 3 other ones that are not in the E. And therefore,
Professor, isn't spade another symbol?
what do you mean symbol? Yes, it is. The black.
So how could a spade and a queen occur at the same time?
Spade is one of the 4 kinds, right? There are 4 kinds of cards. Spade is one of them. And within each kind, there's a queen, one queen. Okay, so there is a queen of spade.
Okay, yes, sorry. I got confused with the queen and I keep including a heart for some reason. I'm sorry.
All right, okay. So there are 4 queens altogether, and spade has 1 queen. And so there are 13 cards in E, event E. There are 3 cards that are in F, that are not shared with the E. 1 card is shared with the E. So can you see that E union F has 16, 13 plus 3? Everybody see that? Okay. E has 13, F has 4, but 1 element is common. So therefore, 13 plus 4 minus 1 is the actual count of the union, which is 16. So there are 16 elements in the union divided by count of the sample space. You're taking 1 card randomly from 52 cards.
52.
52 is the count of sample space. So 16 over 52 is your probability, and you'll have to reduce that. And that's your part B. Part C is what is the probability of the event card is neither spade nor queen? Okay, can somebody tell me how to find that?
Wouldn't that be complement?
Yes, that's complementary event of E union F.
Yes.
That's complement of E union F. So basically we need probability of E union F bar. That's what we need. So that will be 1 minus probability of E union F, 4 over 13. So 13 minus 4, that's 9 over 13. That's your answer for that. Okay, so moving on to exercise 21.
Professor, where did we get 4 from, if you don't mind me asking?
I reduced the 16 over 52 by 4. 4 divides 16 into 4, and 4 divides 52 into 13.
Oh, if we were to just use 1 minus 16 divided by 52, could that be correct as well?
That'll be correct, but then you had to
Okay.
produce the new number.
Okay.
Okay. All right. Going to 21, exercise 21. It says Jason had only 2 job interviews, only 2 interviews he got, and he estimated that he has probability 0.6 to get job A, probability 0.5 to get job B, and probability 0.2 to get both. And what is the probability that Jason doesn't get job A? All right, part A. Can somebody tell me what to do? Probability for Jason to get job A is 0.6. Probability to get job B is 0.5. Probability for getting both is 0.2. The question right now is, what is the probability that Jason doesn't get job A? Anybody?
0.6.
No, there's 0.6 probability for him to get job A. And the question is, what is the probability that he doesn't get job A?
Is 0.4.
0.4. Remember the complementary event, probability of complementary event is 1 minus probability of the event. So we need probability of E bar, complement of getting job A. That's equal to 1 minus probability of E. So 1 minus 0.6. So that's equal to 0.4. Okay, you had to remember that formula. Probability of E and probability of E bar add up to 1. You learned it twice, once in set theory and now in probability theory. It's the same rule. So and therefore I'm applying that formula to find probability of E bar. So probability of E bar is 1 minus probability of E, and that's 1 minus 0.6. And the part A is the complement. I hope you can see that, because Jason gets job A. If that's the event E, then Jason doesn't get job A. It's the complementary event. Okay, part B. What is the probability that Jason will have a job? Well, he only had 2 interviews, so the only way he can have a job is by getting job A or job B. So basically we need to find the probability of getting job A or job B. So probability for get job A.
0.9.
No, not quite. It's not 0.9. For get job A or get job B. Okay, so that basically the same as probability. If I call the event of getting job A as A, then event of getting job B as B, then A union B is the event we need the probability of, right? And probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So that's the intersection you forgot to subtract. Okay.
Yes, I forgot to subtract the intersection.
Right. So it's 0.6 plus 0.5 minus 0.1. No, 0.2, I think. Yeah, 0.2 to get both. He has probability of 0.2 to get both. So that's the intersection. Okay, so 0.11 minus 2.9. So probability to get job, probability to have a job is 0.9. Part C is, what is the probability that Jason will not have a job? What do I do?
0.1.
0.1. Why? Because it's complement to getting a job. So probability for getting a job is 0.9. So probability for not getting a job is 0.1, complementary probability. Okay, now it says Jason will have job B, but not job A. Okay, for that, we have to go to Venn diagram. I'm going to clear part of the screen. Okay, and okay, so let's put these numbers on Venn diagram to be able to answer the next question. Getting job A, I'm going to call that event A. Getting job B is event B. And we already know the probabilities, 0.6 for this, for event A, for event B is 0.5, intersection is 0.2. Okay, so therefore the left section of section of A is 0.4, the right section of B is 0.3. Okay, so the question now is, what is the probability that Jason will get job B but not job A? We'll get B but not A will be this section, part of B that's outside of A. So that's answer is 0.3. D is 0.3. Part E is Jason will have one or the other job, but not both. Okay, can somebody answer that?
0.7.
0.7. He will have 0.4 probability to get A, but not B. 0.3 probability to get B and not A. So 0.4 plus 0.3 is the probability to get A or B, but not both. So 0.4 plus 0.3 equal to 0.7. Okay, so that answers all of that. So depending on the question, you may have to go to Venn diagram. As you can see, we answered part A, B, C without using Venn diagram. And then for the remaining part, we went to Venn diagram. So that's very commonly the case. Exercise 22, from past data, it is known that the probability that a student passes English is 0.7, math component 0.6, and passes neither with 0.1. All right, so that's clearly Venn diagram problem. Okay, so let's do the Venn diagram. English component 0.7. So English 0.7, math component 0.6, and 0.1 to pass both. No, to pass neither. So 0.1 is outside. Okay, so can somebody tell me how to proceed to find all the sections?
We should add 0.7 plus 0.6 plus 0.0 plus 0.1 minus x equals to 1. And we should find the x then, which would
Okay,
be the
yeah,
intersecting part.
yes, I see what you mean. If you call the intersecting part x, oops, I picked up the wrong tool here. Hold on. Okay, so the intersecting part, you said call it x, then apply the union rule, right? Probability of E union M equal to probability of E plus probability of M minus probability of E intersection M. Okay, so that's E union M we know already, no, well, E union M is, what is probability of E union M? Anybody?
0.9.
0.9, because it's outside is 0.1. Outside the two circles is 0.1, so inside my 0.9 because your sample space has probability 1. So the union of the two circles have 0.9. So that's equal to 0.7 plus 0.6 minus x. So from that, 0.9 equal to 1.3, 0.7 plus 0.6, 1.3, 1.3 minus x. So x is equal to 1.3 minus 0.9. I move the x to the left and then 0.9 to the right, and that gives me 0.4. So therefore, intersection is 0.4. Yeah, that's one way. Once you find the intersection, you can find the left side of the E and the right side of M. Another way is to apply the same method I just used in the previous problem. Since the E union M has 0.9 probability, and this part is equal to 0.7, I can find the right side of M. What is it?
0.3.
0.3. Not 0.3. E union M is
Oh, I'm sorry, 0.2. I thought we were talking about E.
Right, okay. E union M is 0.9 and all of E is 0.7. So if I take away 0.7 from 0.9, that'll give me this side, 0.2. So you can do that first, and then 0.2, if you take that 0.2 away from 0.6, that'll give you the intersection, which is 0.4. But we found the same number here. So either way is correct. You apply whichever you're comfortable with. So once you find the intersection, you can find all other sections. 0.7 minus 0.4 is what the left side of E is, and it's 0.3. So now we have all the sections available. So we can go to the questions. First one is the student passes both. Okay, what's the answer? Probably 0.4, right. What's the probability that the student passes English but not math?
0.3.
0.3 is right. What's the probability student doesn't pass math?
I think that's gonna be 3.4 plus 0.1.
You mean, you said 3.3? Did you mean 0.3?
Yeah, I think it's gonna be 0.3 plus 0.1.
Right, the 0.3, the left side of E and the outside of the two circles, that's right. Those are the ones outside the M. So student doesn't pass math means complement of M. Everything outside the M has the probability of 0.3 plus 0.1. So 0.4 is the answer for the part C. Okay, so, there are more questions. What is the probability that the student passes one or the other, but not both? Oh, wait, one or the other or both. Okay, what is that?
Would that be phi? Or would that just be sample space?
0.9.
No, sample space, it is not. One or the other means either English or math. The outside means passing neither, right? 0.1 is the probability for passing neither.
Oh.
Passing one or the other means E union M, isn't it? So that'll be 0.3 plus 0.4 plus 0.2, agree? So 0.9. One or the other or both, that means union. Student passes one or the other, but not both.
0.5.
0.5. The 0.3 plus 0.2. That's right. Okay, next question. If 340 students take the test, how many are expected to pass both components? What should I do to get the answer?
0.4 times 340.
Right. The probability to pass both is 0.4. And if you multiply that by the total count of students taking the test, that'll give you the number of students who will pass both. That's called the expected value. We learned that in the last class or the previous class. So multiply those two to get that answer. If 340 students take the test, how many are expected to pass English only? Okay.
0.3 times 340.
English only, yes, 0.3 times 340. That's right. Only the probability for passing English only is 0.3. So you need to multiply that by 340 to get the answer. Okay, very good. Moving on to the next question. Anne has taken statewide test that contains math component and English component. She estimates the probability to pass math is 0.7, passing at least one. Okay, so let's put that on the Venn diagram. This is similar to the previous question, but it's worded differently, so we should see how to do it. Passing math is 0.7. Probability for passing at least one of them is 0.8, and probability for passing both is 0.1. So 0.1 is given for passing both. Math, and the other one is English. Probability for English is not given, but probability for passing at least one of the components is 0.8. Okay, so how do I translate that? Probability for passing at least one of them.
The union of M and E.
Union, exactly, because passing at least one means passing one or the other. That's what it essentially means. So one or the other or both, you know, at least one means one or the other or both. So that's union. So therefore, probability of E union M is given as 0.8. From that, we can find the right side of E, because E union M is 0.8, and this part M is 0.7. So if I subtract 0.7 from the union, that'll give me the right side of E. So that's 0.1. So intersection is already given. So now we can figure out the left side of M as 0.7 minus 0.1, which is 0.6. To figure out the outside, okay, anybody can tell me what is the outside is? Probability for the outside.
0.2.
0.2. Okay, because the sample space has probability 1. Okay, so that question is, what is the probability that he will pass English component? She will pass English component. What's the answer?
0.2.
0.2. The 0.1 here and the 0.1 here add up to give you the probability of E. And that's 0.2 is the answer to the question. All right, so let's move on to arts now. Those application problems are enough for you to be able to handle any application problem. I have covered all the different kinds. Usually the words have to be translated into set theoretic symbols. Like this, in this case, probability for passing at least one component is 0.8. That translates to union, probability of the union. In the previous one, the probability for a student passing neither, that's complement of the union. So if you properly translate that, there's nothing else that's different in these problems. Okay, so let's go to arts. Arts is just another measure of how likely something will happen in the future. So it's just a different measure of the likelihood of an event. And I'm going to define what that is. Odds for some event happening or in favor of an event happening is equal to probability of that event divided by probability of the complement. So basically, by doing this odds, we are looking at event happening and event not happening. We are comparing those two numbers as a ratio. What is the likelihood that it'll happen as opposed to not happening? So that's essentially what it is. So odds in favor of E would be probability of V over E bar, probability of E bar. Odds against is not happening as opposed to happening, the opposite comparison, same as probability of E bar divided by probability of E. So it's basically a reciprocal of the odds in favor. So odds against is reciprocal of the odds in favor. So you don't have to usually do calculation of both. If you have one, then the other one is just the reverse, reciprocal. But we don't write them as fractions, we write them as ratios. So if the probability of E over probability of E bar comes out to be 2/3, then we say the odds in favor of E is 2-3. We write 2-3 and we read it exactly that, 2-3. So that means, so what does that mean? If you compare the probability of the event happening as opposed to not happening, it'll be 2-3. So 2 chances for the event to happen as opposed to 3 chances for not to happen. So chances of not happening is more. So that's what 2-3 means. So it gives you an estimate, a measure of how likely the event will happen. So you must write it as a ratio. Okay, so let's do the example 8. It gives you the probability of E and asks you for the odds for E and against E. All right, I'm doing example 8. Probability of E is 0.2. And to be able to figure out the odds, I need probability of E bar. What is that? Anybody?
0.8.
0.8. So therefore, odds for E would be probability of E divided by probability of E bar. And that's equal to 0.2 over 0.8. And when you have 1 decimal digit in the numerator and same in the denominator, it will become equal to 2/8, because you can say you're multiplying numerator and denominator by 10. Then both will become whole numbers, 2/8. You have to reduce that. 2 divides both, so 1/4. And so you present your answer as 1 to 4. 1:4, colon. If you enter the 2 to 8 as your answer, that'll be wrong. WebDesign will mark it wrong. You have to reduce it and then present the answer. So 1:4 is the odds 40. So problem is also asking for odds against. And where would that be?
4-1.
4-1, just the reverse of that. So you can just always, no matter what the question is, you can find the odds for and then reverse it for the opposite question. All right, exercise 24. That's an exercise you're supposed to be doing it, but I'll do it with your assistance. Probability of E bar is given as 3/5. So that means I need to find probability of E to be able to answer any question about odds. Okay, what do I do?
It's 2/5.
2/5, because it's 1 minus probability of E bar. Probability of E, that is 1 minus probability of E bar, because probability of E and probability of E bar add up to 1. So if you want either one of these, you subtract the other one from 1. So I need probability of E right now. So the rearrangements of this equation will be 1 minus probability of E bar is probability of E. So 1 minus probability of E bar is 1 minus 3/5, which is 2/5. Okay, so we have the probability. So let's find the odds in favor of E first. Odds for E is probability of E in the numerator, 2/5 divided by 3/5. Now you learned how to divide fractions. It's 2/5 times reciprocal of the denominator, 5/3. And the 5's cancel out. I'm getting 2/3. So therefore the answer is 2, 2, 3 for first part. Part B says odds against E, that'll be 3 to 2. Okay, let's do the 25. Let me clear the board. All right, I'm doing 25. 2 coins are tossed. Find the odds for 2 heads. Well, you have to find the probability. You already learned how to find the probabilities. Exercise 25. 2 coins are tossed. So we know the count of the sample space is going to be code words with T and H's, right? But there will be 2 letter code words. All they're going to be head, head, tail, 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 head, head, tail, right? Without having to write all that, we can count it. So there are 2 ways to fill this, head or tail, 2 ways to fill the second one. So there are 4. And then find the odds for 2 heads. So part A is asking for 2 heads. So the event is
2 out of 4.
Why do you think there are 2 elements? What element in the sample space will make this event happen? It says,
It's 1 out of 4.
yes, but can you answer the question, this question first? What is the
It
element?
would be head and head.
Head and head, HH. That's the only element of the sample space that'll make this happen. So there are no 2 elements. There's only 1 in the event, right? One student thought there will be 2 elements. That's not right. So there's only 1 element that will make the event happen. So probability for that event is 1/4. For this event, E to happen. Probability for the complement to happen is 3/4. And therefore, odds for E would be 1/4 over 3/4, which is equal to 1/3. So 1 to 3 is the answer to the question. Part B says, what are the odds for exactly 1 head? Okay, the event F will be having one head. What are the elements that will make this event happen?
Tail and head and tail.
Right. Only 2 elements will make that happen. So probability for this event is 2/4, 1/2, and probability of F bar is also 1/2. So odds for E would be 1/2. So that'll be 1 to 1, 1/1. Both cancel out. So 1 to 1, they say. That means there are equal chance for both. 1 to 1 means equal chance for having 1 head and not having 1 head. Okay, part C says at least 1 head. What are the elements that will make that happen?
Head, tail, and tail, head.
Right. 3 elements. So probability for G is 3/4. Probability of G bar is 1/4. So odds for G will be 3/4 over 1/4. That'll be 3 to 1. Okay, going over to the question 26. A card is drawn from a deck of 52 cards. What are the odds against diamond or king? What are the odds against getting diamond or king is the question. So we need to start with the event of getting diamond or head, diamond or king. Okay, so can anybody tell me how many elements are there in the event of diamond or head?
16.
16. Very good. Diamond or king. We already counted that in a previous problem, in an earlier problem. That was spade or queen. It was. So it's similar. This is similar. Diamond has 13. There are 13 diamonds, and this event of king has 4, but 1 is shared. So therefore, 13 plus 4 minus 1 is the correct count. And that's equal to 16. So count of E is 16. So therefore, probability of E is 16 over 52. Probability of E bar is 1 minus that. So if I
I'm sorry, how did we get the number 16?
okay, there are 13 diamonds. Oh, okay, sorry. Okay, there are 13 diamonds, right? So if I write diamonds, there are 13 elements here. If I write all the kings, there are 4 of them. How many are shared? 1. The diamond of king. There's 1 diamond of king. So that 1 is shared. There are 3 others. Okay, so 13 plus 1 plus 3, 16. Are you following me?
Yes.
Hold on. It's 13. It's not 13 plus 1. It's 12. Sorry about that. There are 13 elements altogether in the D, and 1 is shared. So 12 here on the left side. And altogether 4 kings are there. 1 is shared. So 3 of them are outside. So that's why I have these numbers. So 12 plus 1 plus 3. That's what the 16 is. Okay, so 16 over 52. I'm reducing it by 4, so I get 4 over 13. So probability of E bar is 1 minus 4 over 13, and that's 9 over 13. So therefore, odds for E would be 4 over 13 over 9 over 13. That will be 4 to 9. But the question is, what are the odds against diamond or king? So odds against equal to 9 to 4. You know, always you just work with the odds for the event, and then you can reverse always. That's the easiest way.
How do we put 9 to 4? Wouldn't it be like 13 to 9?
I'm not following the question. You just write 9 to 4 this way. That's how you present the answer.
No, I was just asking how did we get 4 and 9 as the ratio?
Oh, how? Because the probability for the event E occurring is 4 over 13. And probability for E not occurring, E bar occurring, is 9 over 13. So odds for E would be probability of E over probability of E bar, which is equal to 4 over 13 over 9 over 13. I skipped all this math. 4 over 13 times 13 over 9 will be 4 over 9. Okay?
Okay.
Right. 4 over 9, and we write that as 4 to 9. And so odds against is just the reverse, 9 to 4. All right, so now I'm going to have to do a little theory here, because the next question is about finding, going the opposite way. if they give you the odds, how do you find the probability? That's the question next. We have seen how to find odds when the probability is given. We have to go backwards now. So probability of E is the question given odds for E. So odds for E is given as a ratio. So let's say I'm going to have to work out the theory. So let's say odds for E is A to B, given number. So these are just given numbers, but I'm going to use these symbols to represent them. If those two are given, then how do you find the probability? This is given, so what is probability of E is the question. So if I call probability of E as X, what I'm going to work out is the theory of how to find the probability by using odds. But if you don't really, if you don't understand the work I'm going to do, you can still use the answer as a formula, but if you understand the work I'm doing, then you will understand the whole thing better. So I recommend trying to understand it. So if the probability, if I call the probability as X, then I need to find a formula for the X in terms of A and B. A and B are the given numbers. So I need to find a formula for the X in terms of A and B. So if the probability of E is X, then probability of E bar, I can write an expression for it. What would that be? Probability of E is X. What is the expression you can write for probability of E bar?
1 minus x.
1 minus X, very good. Because probability of E and E bar add up to 1. So therefore probability of E bar would be 1 minus X. Now I'm going to write the odds using these numbers. Odds for E will be probability of E over probability of E bar. And so that's equal to X over 1 minus X. That's X over 1 minus X in terms of the probability we assumed. You know, we said probability of E is equal to X. So in terms of X, I have written an expression for the odds. Now this expression, X over 1 minus X, must be equal to A over B, because A over B is the odds for E. So therefore, both of these should be equal. From this formula, we can find the X. From this equation, we can solve for the X. To solve for the X, I had to multiply by the denominators. If I multiply both sides by B, then I get a BX here, and the B's cancel out on that side. And then I'm also going to multiply by, so I have now bx over 1 minus x equal to a. I also need to get rid of the denominator on the left side. So I will multiply by 1 minus x on both sides. That'll eliminate that. So I have bx equal to a. If I distribute the a inside this, I get a minus ax. Okay, I'm trying to solve for x, remember? So I'm trying to find x in terms of a and b. So I need to bring the x's together. So this minus ax on the right side, if I add ax to both sides, then it'll come to the left side. So I have ax plus bx equal to a. These two cancel out, so I have a. If I factor out the x from the left side, then I have x times a plus b equal to a. Finally, to solve for x, I just have to divide by this, a plus b. So divide both sides by a plus b, then x equal to a over a plus b. So what I have proved here is probability of the event. If the odds for the event is a to b, then probability for the event E is a over a plus b. So from the ratio they give you for the odds, you can find the probability. So if the odds is given as 2 to 3, then odds for E, then probability of E is equal to what?
2 over 5.
2 over 5. As simple as that. A over A plus B. This number divided by sum of the both numbers. That's what we proved. If the odds are A to B, then probability equal to A over A plus B. So if the odds are 2 to 3, probability is 2 over 5, 2 over 2 plus 3. That's simple. And always, if you need the probability of E bar, that'll be 1 minus this. So that's always there. So no matter what the question is, go ahead and find the probability of E and then find E bar if they ask for that. So this is something you need to remember. Probability of E is equal to A over A plus B if A to B is your odds. Okay, so let's see if you can answer this one. Exercise 27. It's the same two students answering all the questions. The others should participate too. Exercise 27 says the odds for Jamie passing his math test is 3 to 7. What is the probability that he fails and probability he passes? Let's start with the pass. Odds for passing is 3 to 7. So probability for passing can be found directly from that. What is that?
3 over 10.
3 over 10. So that means probability for failing would be
7 over 10.
7 over 10, which is 1 minus 3 over 10. Okay, very good. That's all there is. Just apply the formula whenever you need to find probability from odds. It's just A over A plus B. But you had to remember, if the odds for E is given as A to B, then probability for the event E happening is A over A plus B. So don't do the opposite way. You had to have the odds for E to find probability for E. And then you can work out the probability against E from that. All right, so that finishes that. And we need to...
Professor, what's the answer for A again? I'm sorry.
For which one? Part A?
For example, yeah, for part A.
To answer part A, I would begin with the part B because the odds given to us is for the event. Odds for the event is given as 3 to 7. So therefore, odds for passing the math test is 3 to 7. So therefore, probability for passing, which is part B, can be found directly as 3 over 10, 3 over 3 plus 7, right?
Yes.
Okay, so once you do that, you can find the probability for failing as 1 minus that number, 1 minus 3 over 10, which is 7 over 10. Okay, answer for part B is 3 over 10. Part B, 3 over 10. So part A, probability for failing.
Hey, when you would solve it though, wouldn't it be confusing to do 1 minus 3 over 10? Wouldn't that be thought to be 2 over 10 then?
Where are you getting 2 from? 1 minus 3 over 10. If you do the subtraction, that'll be 7 over 10. Where are you getting 2 from? Okay, are you confused about this subtraction?
Yeah, I was just looking at the fractions and I was just thinking about like when we're subtracting fractions.
Okay, 10 is the common denominator. Or you can say you're writing 1 as 10 over 10 minus 3 over 10.
Yeah, right now I just put it into the calculator as dividing it by the whole decimal.
But
I
the
got 0.7.
to give you decimal numbers, but we want to do fractional arithmetic and enter fractional numbers. Not all the problems will accept decimal answer. And that's why I'm doing fractional arithmetic. So you can write the 1 as 10 over 10, And then the 10 is the common denominator, and the numerator is 10 minus 3. This 10 minus 3.
Okay, when we're doing the fraction with 1, could we always put 1 as 10 over 10?
Yes.
Okay.
Whatever the denominator for the second number is, you want that number here in the numerator and denominator.
Okay, so then any number that's in the second denominator would be in the first numerator and denominator to subtract from.
Yes, because
Okay.
one is equal to 4 over 4, 5 over 5, 6 over 6. All of those are 1.
Okay, thank you so much.
You're welcome. Okay, so all right, so that finishes that. I'm going to close that and go over to the next one, which is worksheet 10. We need to learn to apply counting techniques. We did some of it before, but we need to do more. So the problems we have been doing so far did not require counting techniques, except a few, like tossing 5 coins and things like that. We did a few, but there are other problems that will require counting techniques. So let's do some of those. I'm going to begin with this example 1. From a deck of 52 cards, 1 card is taken. Now, if you take 1 card, then you don't need counting technique, because it's very clear there are 52 possible cards when you take 1 card. So the count of sample space is 52. So I'm doing this example 1 first to show you in what circumstances you don't need to use counting technique. If I take 1 card from 52 cards, then the count of the sample space is 52. So that's very clear. And then it says, what is the probability that it is a spade? So the event is the card is spade. And again, we don't need counting technique. Count of E is 13, right? There are 13 spades. So what is the probability that the card is a spade? It's 13 over 52. Now, here we didn't need to use counting technique, but if you take more than 1 card, then you need counting technique. So let's see the example 2. From 52 cards, 2 cards are taken. What is the probability both are spades? Okay, now we need counting technique. If I take 2 cards from the 52, then it can be Jack of spade and king of diamond, that's one possibility, and ace of spade and king of diamond is another. So there are so many of those, but I can count them using the counting techniques we learned. In other words, the count of the sample space in this case would be same as number of ways of choosing 2 from 52. From the 52, in how many ways can I take a combination of 2? And clearly, the rearrangements are not different ways of having 2 cards. So it's just the rearrangements are not counted. It's just, that means it's combination. Combination of 2. In how many ways can we get a combination of 2 is the question. So that's C of what numbers?
52, comma 2.
Right, 52, comma 2. So that's the count of sample space, number of ways of choosing 2 cards. Okay, so that will have to be simplified as factorial 52 divided by 52 minus 2 is 50 factorial times 2 factorial. And this part simplifies to 52 times 51. Everything after that will cancel with the 50 factorial. And I still have factorial 2. That will be equal to 2. 2 divides the 52 into 26. So I need to multiply 26 and 51. And I'm doing that in my calculator right now. And that gives me 1326. So that's the count of sample space. The event that we are trying to find probability of is both are spades. Okay, so that means if I want to try to write some of those, it'll have to be two of spade and king of spade, right? Both have to be spades. And 2 of spade and 3 of spade, or ace of spade and queen of spade, and keep going. Now you get the picture. Both have to come from the spade. And how many cards are there in spade? How many spades are there?
13.
13. So how do I calculate the count of these? Count of
Is
E.
it 13 times 13?
No. 13 times 13. I'm trying to think why you are thinking that. You're thinking that first card can be any 13, second card can be any 13.
Yeah.
Not really. And also you're trying to apply box method, but box method will count number of ways of arranging them, but we're not arranging them here, right? So you cannot use box method. And also if you use box method, if you put 13 here, then you have only 12 for the next one, isn't it? Not 13. You have already, right, already placed one in here.
Can you explain more about what you were doing for the set of E? Putting 2K, 2, 3, and A2?
Okay, I just wrote some examples of the cards that we need to have. The E should have both cards spades. Both of them should be spades. So that means, what are the possibilities? 2 of spade, the 2 of spade. Let me write an S for spade.
Is it permutation 13 too?
No, it's not permutation, because we are just taking the 2 cards have to be spades. They don't have to be in any order. The order doesn't matter here. You're not
It's a combination.
combination, not permutation.
Yeah, because
Okay, it's a combination of what are the numbers again?
13,
13 and 2.
13, 2, exactly. Because there are 13 spades and all the different ways of combining 2 cards, taking 2 cards from 13. That's what the count of E is. So I was writing down some of them, like 2 of spade and king of spade. If I combine them, that's one of those, right? And then 2 of spade and 3 of spade. Remember, within the spade, there are these ace, and then 2, 3, 4, 5, all the way to 10. And then also you have king, queen, and jack. Those are the 13 cards. Okay. So 2 of spade and king of spade is one combination. 2 of spade and 3 of spade is another. And so these are I was trying to explain to you that these are combinations of 2 from the 13 spades, from the 13 cards. So to count them, we cannot write them all down, but we can count them. To count them, we just have to say, how many ways are there to choose 2 cards from the 13 spades? And that's equal to C of 13, 2. I was trying to explain that by writing these. You don't have to write any of that, okay? You only have to count them. So now I have the count of E. So let me simplify that count.
would you need it still in the combination form, or would you need it in the actual number?
Number. We need to find the number.
Well, I think I found it, and it says 78.
Okay. Let me do that myself so that everybody can see how that simplifies. Some of you may have forgotten the counting formulas, so I want to recall that. Factorial 13, factorial of this number divided by 13 minus 2 factorial, which is 11 factorial, times 2 factorial. So 13 over 11 factorial will simplify to 13 times 12 divided by 2 factorial is just 2, 2 times 1. 2 divides the 12 into 6. So 13 times 6 will be your answer. 78. Yeah, you have the right number. Very good. So therefore, the probability for that event is 78 divided by 1326. That's our probability. So as you can see, you need to use the counting techniques we learned before. So let me do the second part of that. So second part, we have the count of sample space. The second part says one is a spade and the other is a diamond. Okay, so the event F is going to be one spade, one diamond. So that means first one has to be chosen from the 13 spades. So if I want to write that as a combination, how many ways are there? C of
13, 1.
13, 1. From the 13 spades, we need to choose one spade. And one diamond, the number of ways of getting that will be a combination of
13, 1.
1. And therefore, the product will be the answer. The multiplication rule applies. You are combining each one in this collection to each one in this collection to get all of the different ways. That's when the product applies, the multiplication rule. Now this is 13, 1 is 13. If you remember the fundamentals we learned in the counting techniques. C13, 1 is 13. So 169. Okay, so probability for F is 169 divided by 1326. Okay, let's go to exercise 1. It says, oops. 11 white socks and 6 red socks are there. 11 white, 6 red. 2 socks are selected at random. What is the probability that one is white and the other is red? Okay, first we have to count sample space. We are selecting 2. So count of the sample space. Can anybody tell me what that is?
Combination of 17, 2.
Combination 17, 2. Very good. The 11 white and 6 red are there, but when you select 2, it's going to come out of all 17. It's going to be any 2 from all 17. So number of ways of getting 2 socks from those is C72. So that'll be the count of the sample space. So let's simplify that. That'll be factorial 17 over 17 minus 2, which is 15 factorial times 2 factorial. So 17 times 16 over 2. 2 divides the 16 into 8. So 17 times 8 is your answer. 56, 136. Okay, so now that's the count of sample space. Now for all these questions, the first thing you need to do is counting the sample space. Then go to the actual event. The event E is 1 white, 1 red. Okay, can somebody tell me the count of that?
Combination of 11, 1 times combination of 6, 1.
Right, we are choosing 1. So first one has to come out of the white ones. 11 white ones are there. Second one has to come out of the red. So that's 11 times 6 equal to 66. So the probability for that event is 66 over 136. Part B says both are white. What is the probability that both are white? Okay, so both white is our event, and we need to count this event. Okay, can somebody tell me what that is?
Combination of 11, 2.
11, 2. So both socks have to come out of the 11 white ones. So a number of ways of getting that is C11, 2, which is factorial 11 over factorial 9 times factorial 2 equal to 11 times 10 over 2. 2 divides this into 5. So we have 55. The probability of that is 55 over 136. There's one more part which says both socks are of the same color. So now it's not necessarily both white, not necessarily both red, both have to be same color. Okay, so how do we do that? We still have the same number for the sample space. Let me try to squeeze my work into this. Okay.
Is it combination of 11, 2 plus combination of 6, 2?
Yes, very good, excellent. That's exactly right. So let me explain for the others why that's the case. It says both are of the same color. That means we had to translate that event by writing it. I had to write it down clearly. The event G, I'll call it, is both white or both red. Isn't that what it means? Both have to be of the same color. So that's what it means. So that means it's a union. So count of this G is count of this event, union count of this event. And so count of both white is C11, 2 whites. And OR corresponds to union, so therefore plus. Remember, count of A union B is count of A plus count of B minus count of A intersection B. But these are mutually exclusive. Here you have both white, here you have both red, so there's nothing common, and they are mutually exclusive. So therefore, the intersecting part is empty, and so this is our formula. So count of 11, C11, 2 plus C, what's the number?
6, 2.
6, 2. Okay, thank you. So we need to simplify them. 11 over 11 minus 2 is 9. 11 factorial, 9 factorial, 2 factorial plus 6 factorial over 4 factorial, 2 factorial. Okay, so this part simplifies to 11 times 10 over 2 plus 6 times 5 over 2. Let me clear the bottom. Okay, so that's equal to 2 divides the 10 into 5, so 55, plus 2 divides the 6 into 3, 15. Okay, so probability of G is 70 over 136. Okay, so well, there is another example I have, actually more than one example. All right, we're out of time, so I'm going to stop here. I will have problems limited to what we have done so far.